What's up guys, welcome to my channel, and today we're looking at the searching for MobileNetv3 paper. So paper from the MobileNet family developed by Google. So why I'm reviewing this paper? So basically I see a lot of reference from the EfficientNet to the MobileNet. When I analyzed the whole MobileNet papers, I saw the whole progression towards EfficientNet. So that's what I want to show you today. And yeah, we can start from the MobileNet v1. In the first paper, the MobileNet v1, they introduced two things. Basically, the whole MobileNet's paper, the whole MobileNet's models were developed to find a balance between accuracy and performance. So the main point was to improve the accuracy while keeping the latency and complexity of the model low. Latency is basically how long it takes for the model to produce the output. Okay, so MobileNet v2 introduced two things. First of all, they use depthwise convolution, and they developed like the whole new block for it. So they use depthwise convolution, which is extreme version of group convolution. So if you're not familiar with it, it's basically, imagine if you have 32 input channels and the output is 32 output channels, right? So normally we would get one filter that goes to the one filter from the input, and then to the second one, and then to all filters in the input. And then at the end we sum them up, and that's how we get one filter in the output. So what they do in the depthwise convolution, they basically take one channel, one filter over there, and they only use the one channel from the input. This only looks at the one channel, the second one only looks at the second channel, and so on. This hugely speeds up computation. Yeah, so what they did is basically they replaced the regular convolution with depthwise convolution. So they operate obviously on the same input, the same number of channels. So when we have 32 channels, so when we got 32 channels as an input, we got 32 as an output from depthwise convolution, and then one-on-one convolution gives us the output channels we want, right? So that's the one thing. Another thing, they introduced the alpha and rho parameters. So alpha is a width multiplier. So what you can do with it is basically you can multiply by alpha every channel in the network. And what they introduced that they basically, you choose the alpha from 0 to 1. So this is the parameters for 1. And you can reduce the number of the complexity of the network by using the alpha parameter, and you can adapt it to whatever application you have. And I also introduce rho parameter. So rho is responsible for the resolution, so you can multiply the resolution and also basically reduce it. That was basically really important in terms of bringing this deep learning models to the mobile devices. So that was the goal basically of the whole MobileNet, because it's all developed by Google. They didn't want to just keep it in an academic environment. They wanted to bring it to the mobile. MobileNet v2 introduced also two things. So first of all, they improved the bottleneck, like the building block. So instead of having a separable convolution block, as we had in the MobileNet v1, they introduced bottleneck with expansion layer. Okay, so it looks like this, but I'm gonna use this example, which is much easier. They also have residual connection only when the stride is 1, and obviously the input channels are equal to output channels to not make any projections. Because if you make another projection, it just adds more parameters, so it wouldn't make any sense. Another thing is they use convolution first. They use ReLU 6, which I'm gonna explain later. Then they use depthwise and 3-on-3. Then they use convolution 1-on-1 without ReLU. Because of the property of the ReLU, it was dropping so many information, and they find out empirically that without ReLU in this layer, it performs much better. Another improvement that they bring is also alpha and rho beyond 1. So you can actually increase the network or decrease the network. And that was really important, because that's when we started to really play with the networks. And that's what you see actually in EfficientNet when they completely have the 8 different models. So that's the key parts that they had in MobileNet, in the previous MobileNets. And now we can move to MobileNet v3 and what improvements they had. So to start with, they claim this paper starts exploration of how automated research algorithms and network design can work together to harness complementary approaches, improving the overall state of the art. Through this process, we create 2 new MobileNet models for release, MobileNet v3 large and MobileNet v3 small. We've got 2 models there, obviously small and large, And the main, I think the point of this paper is they don't manually create the network. They use neural architecture search to actually find it. So that's really interesting, and I'm going to get to this later. But to start with, I'm going to show you what they improve in terms of the building block. So first of all, they have NL here, which is activation function. So basically non-linearity. And the non-linearity, basically the activation is changing throughout the network. We're gonna get to it later. It's pretty much follow the same convention from the MobileNetv2 to this point. Here they introduced the squeeze and excite block. And what is this? If you want to see the whole paper, squeeze and excitation, you can check it out on my channel. But I'm also gonna give you a brief explanation how it works and why it's basically here. In a nutshell, squeeze and excitation block is an attention mechanism that points out the channel that we need to pay attention for certain input. So if you think about it, we look for the different features when we pass the plane and for the cat. So in order to maximize which channels we should pay attention to, we got the squeeze and excitation block. What it does, it basically takes an input, which is height, weight, and channels. So this is after residual mapping. And then what we do is basically we use global pooling to squeeze all this information to one value per channel. So you can see one on one channel. Then we got fully connected layer that basically finds the connection between channels. So R is a parameter that we control the complexity of the model, and obviously we want to reduce the number of parameters here. So then we got ReLU that adds nonlinearity to the model. Then we got another fully connected layer, which is again bring it to the size of the channels again. And we got the sigmoid. So sigmoid is scaled down every output to value of 0 to 1. And in this case, each channel has a certain weight attached to it. Maybe when we pass the plane, the value of certain features is higher because of it than when we pass it the cat. It's much lower. So that's the whole idea behind it. And yeah, we're gonna implement it also in PyTorch and in our network. So that's basically the whole squeeze and excitation block. And they also have one thing here. It's called Hard-Sigmoid. And we're gonna get to it. So they add new activation function that weren't used before. Apart from Hard-Sigmoid, they also use a Swish function. So Swish function is significantly improves the accuracy of neural networks. Now let me show you how they look like. This regular sigmoid in the dashed line, and Hard-Sigmoid is basically ReLU. ReLU which is cut off at 1 and slightly moved to the left. And Swish, and why we actually use Swish. So derivative of ReLU function, when we do the backpropagation, we get 0 or 1. So in many cases we end up with the dead neurons that never actually got updated. And Swish is leaving this a bit of amount of information. So basically if the values below 0, it still get updated a bit. So it prevents the dead neuron. Okay, but so how we calculate Swish? Swish is calculated by input x times the sigmoid of x. But as we know, sigmoid is much more expensive to compute on mobile devices and on any devices. So it's not efficient. So what they came up with, they actually used ReLU6, which is cut off the top of out there and translated by 3. So in this case, they get the sigmoid by using ReLU, right? So they can calculate the Swish by using ReLU, and by this they don't. So they calculate the sigmoid using the ReLU, and in this case they just save computation power, but they also don't have any lose in accuracy. So that's really slick solution, and yeah. So that's only 2 improvements they did. There are few improvements in terms of architecture. So architecture looks like this. This table is a bit. So to start with, they have input, operator, expansion size in the bottleneck. We also got the output channels. SE is basically do we have squeeze and excitation or not. And nonlinearity is basically the function that we're going to use. So they found that most of the benefits Swish are realized by using them only in the deeper layers. So as you can see, hard Swish is used later on in the network. So that's the large model, by the way. This is the smaller model. So we got the nonlinearity. So the kernel sizes vary over the network. At the end, they use NBN, which means no batch normalization. Yeah, and they modified the first convolution and the last ones, and I'm going to show you why exactly. So this is the ordinal kind of way they did it, and this is the efficient last stage. So as you can see, here is just the number of channels is expanding over there, then reduce, and then expand again, right? And they bring the average pooling before actual convolution. So they found that basically this convolution is really important because this layer is critically important in order to have rich features for prediction. However, this comes at a cost of extra latency. So these few layers were really important, but obviously they slow down the network. So what they came up with, if you put the average pooling before, you reduce the size of the input from 7 to 7, for example, to 1 on 1. And when you apply the convolution later on, you have so much less computation if you have 1 on 1 rather than 7 on 7, right? So in this case, this more efficient last stage is able to drop 3 expensive layers at the end of the network at no loss of accuracy. So that's the one change they did. And they also changed the first convolution. They used number of filters. They reduced the number of filters to 16 while maintaining the same accuracy as 32 filters. And this saves additional 2 milliseconds. So it also points out for you how like small details they really pay attention to. So yeah, I think now we can go how they actually found the architecture we see. So this is the architecture they found, and we're going to see how they actually did it. Actually, this part is not, if you're not interested in this part, then it's not really important in terms of implementing it. Feel free to skip it, but I guess it's interesting in the sense that neural search architectures overall are really interesting topic. So yeah, so this is how they found the architecture. First of all, you got the controller. So you can think of it as a kind of generator. So it generates the model, we train it, we check the accuracy, we pass it also the model to the mobile phone, and we see the latency. So this is the two objectives of the model. We want a high accuracy, low latency. And then we compute a reward from it. And this reward goes again to the controller. So based on that reward, the controller is updating and generating new models. The controller itself that gets the reward looks like this. So it's a recurrent neural network. We got 7 blocks. So each block contains few parameters that we're looking for. So first of all, the controller is picking up the operation. So you can choose from depth-wise convolution, and MobileNet block. Then we picked up the kernel size, SE ratio, skip operation. So basically if we did identity connection, pooling, or no skip connection, filter size and layers. So as you can see here, it's picked up the MobileNet block. It used 5 on 5 convolution, 5 on 5 kernel size, SE 0.25. So that's how they basically find the whole architecture. So this architecture is optimized to get the best accuracy and the lower latency. Okay. And another thing they did in order to fine-tune the network, they use NetAdapt. So what it does is basically it takes the pre-trained network from here. So that's our generated network, and we pass the budget here. So what we want, what latency, energy, whatever we want, we pass it to the platform, so basically the phone, and then we change some of the features of a network like filters or layers, right? So we manipulate the width and the depth of the network, but in this case, they actually fine-tune something else. They types of a proposal, so the changes that they want to do to the network is reduce the size of any expansion layer and reduce bottleneck in all blocks that share the same bottleneck size. So that was the two fine-tuning objectives they had for the NetAdapt. Okay, I mean the whole idea of neural search architecture, I think it's really interesting, and yeah, I gave you a little overview about it. But yeah, without further ado, let's go to the Colab and just code it. All right, so I prepared some of the code before because there's no point of writing it again. And we're gonna focus on more important stuff like basically the bottleneck and the whole architecture. I also prepared the configuration of the networks before, and I'm gonna show you what exactly it is. So we got the large configuration, which is basically this. So we got input, operator, expansion size, output channels, squeeze and excitation block, non-linearity, and stride. And I basically rewrite all of it to the Python. And the same I did for the small one. Okay, how it looks like. So first of all, the first argument here is kernel. Then we got the expansion size, in channels, out channels, SE block as a false or true, activation function, and I did define them before to not pass all the time NNN, Hard-Swish and ReLU, and I also pass stride here. Okay, and one thing more, the config doesn't involve the first and the last, so it's only for the bottlenecks. It doesn't involve this. I call it classifier and the first convolution. All right, I hope it makes sense to you. And all right, so let's go to the conv block. So conv block is basically convolution, batch normalization, and activation function together rather than defining it all somewhere in the network. So activation as a default is ReLU. We also got groups, which for dipwise convolution. We also got batch normalization defined as a true, but in some of the cases, as you can see here, we don't have a batch normalization, so I ain't gonna add it, but we still want to have an activation function. So bias is false because we use batch normalization. That's pretty much it. Also, I add padding. Padding is equal to kernel size divided by 2, and what it does is basically when kernel size is 1, we got padding 0. When kernel size is 3, we got padding 1. And when kernel size is 5, we got padding 2. So it's just basically easier than each time passing a different padding because we're gonna use different kernel size in the network. The next thing is we got the squeeze and excitation block. So we only pass the in channels here. The ratio that we downsample it, as you remember, it's defined in the MobileNetv3 as input channels divided by 4. Okay, so that's it. We got adaptive average pooling, fully connected, ReLU. They also use ReLU here, and at the end they have Hard-Sigmoid. So that's basically it. I don't think there's more to explain it. And now we can move to Bottleneck. So Bottleneck is going to take input channels, output channels, kernel size, expansion size, SE, which is going to be true or false, act, which is activation function, and stride. Okay, so let's define it as a block, and we're going to pass it all to NN sequential. So first is conv block with in channels, exp size, so expansion size, kernel size is 1, then stride is also 1, and activation is equal to act, so we're going to pass the activation. Groups is equal to 1, and yeah, the rest is default. Alright, another block we've got is deepwise convolution. So it's also going to be a conv block, but we got exp size as an input, exp size as an output, kernel size, this is going to be the one that we're going to pass, stride is equal the same, the ones that we're going to pass, activation is going to be the same as we pass, and groups is equal to exp size. Okay. So later on we got again, now we got the squeeze and excitation if we have a squeeze and excitation. So we can call it SE block, and we pass exp size, and if SE, so we add a condition on the top of it. So if SE is true, then we pass the SE block, else we pass NN identity. So identity means that we not do anything, basically. So the last thing is conv block again. So it's like pointwise convolution. And we got the exp size, we got the out channels, and we got the kernel size 1 and stride 1. And activation is equal to NN identity. So again, we don't apply any activation. So that's it. We also need to add residual connection. So self add is equal to true when in channels are equal to out channels, and stride is equal to 1. Okay. Then we define the forward function. We also gonna input the tensor and output the tensor. I'm gonna call it res. So self block from x, then if self add. And what we do basically is we add res and x, and we just return res. Okay, so that's basically the whole block. I guess that was pretty easy. And now we got the whole architecture, the MobileNetv3. Okay, so how are we gonna do it? So first of all, we need to start with the argument that we pass is a config. So we either can pass large, so this configuration, or small. So you're gonna iterate over each list in this list. All right. So we also got a config name, and it's simply because if you look at the architectures, both of them, most of this stuff you can basically scale. It depends on the list you have, but they have one different thing. Basically, the large model has 1280 output channels there. A small has 1024, and we need to distinguish them by the large or small. That's why we pass the name. And yeah, we're gonna get to it later. Obviously, we got in channels and classes. Okay, so we can start with first block that we have in our model. So first convolution block, first convolution layer actually, first convolution layer. Okay, so conv is equal to conv block, and it basically has 3 input channels. Output channels is 16, and kernel size is 3, stride is 2, and activation is actually hard swish. So that's the first convolution. Then we're gonna iterate over all of the blocks. So here we're gonna collect all the bnets in one list. So we basically need to write a for loop. So for c in config, and we're gonna get the kernel size, exp size, out channels, se and l stride from 1c. Okay, we basically need to also create an empty list, which is gonna be called blocks. Okay, and we collect those blocks into the list. So self blocks append, so it's gonna be bneck, and we're gonna pass in channels, out channels, kernel size, exp size. So basically the whole arguments we got in the configuration. Then we need to pass activation, which is going to be nl, and stride. Yeah, we got this right. All right, so that's it for this one. Also, it's pretty simple. And then we need to just add the classifier at the end. I'm going to define it as a nn sequential. Okay, so it starts with the convolution, and we also need to define a few stuff. So first of all, we need to define the last output channel. So it's going to be this one, right? Because it's going to be the input for the first convolution, and the expansion size, the last expansion size, is going to be the output channel for this convolution. It's going to be config, so it's going to be 3. And the last exp is going to be config -1 and 1. Okay, that was easy. Also the out channel, so the final out channel here, as they call it, it's different for large and the small model. Out's gonna be 1280 if config name equal to large, else it's gonna be 1024. Okay, so that's why we need the config name for. Okay, so now we can define the whole classifier. Okay, so conv block's gonna be in channels will be last out channel, and the output channel is gonna be last expansion channels, kernel 1, stride 1, and yeah. Then we got adaptive pooling, so it's gonna be nn adaptive average pooling, and the output we want is 1, 1. Then we got another conv block with last exp, and then the output's gonna be out. So that we define. So the output's gonna be out, 1 on 1. Yeah, hard swish again, but we don't have groups as 1, but we don't have batch normalization, so we pass false. And in this case, bias is true, I guess. I haven't checked it. And also we got dropout. So dropout is 0.8. And at the end, we also got another convolution, and we're gonna go define it as a conv2d. And in channels is basically out, classes 1, 1, and that's it. So that's the whole classifier. Now we can actually just write the forward function, and that should be it. So let's do it. Again, we pass tensor and we output tensor. Okay. First we got the first convolution, conv. Then we iterate over blocks in self blocks, and we generate output from each block. And then we got the basically output from self classifier. We also need to flatten it, and that's it. Let's see if it works. And also I wanted to point out 2 things. They also introduced the, as I said before, the row parameter, and they can modify by using row their input resolution. As a default is 220. I ain't gonna modify it, but you can do it using this parameter. Okay, so let's define net. It's gonna be config's gonna be from name. So let's say it's small name. So that's it. And we just pass torch rand 1, 3, 2, 2, 4, 2, 2. Okay, and let's see the output shape. Alright, there were only 2 bugs, and basically I haven't passed the SE over there. I don't know why exactly, so that was in MobileNet blog. Oh no, in MobileNet architecture overall. Okay, it was spelling error in classifier. So that's basically it. And it seems that it works. I also compare it using the torch summary. So here we can see what's the number of parameters that the network has. And in a small model, it has pretty much the same as the state over there. And for the large one, we're gonna see it. So now we're gonna see how much they have for the large one. 5.5 million around it, and in a paper they have 5.4. Alright, that's similar. That's basically the whole MobileNet architecture. It took me a while to actually code it, so yeah, it's a tough one comparing to the previous one I did. Okay, so that's basically it for this video. I hope you like it. I hope you enjoy it and you learn more about the MobileNet, and it gives you a bit of background about the efficient net and MobileNet and the progression of all of it. And yeah, if you like that kind of videos with the reviewing paper and code implementation, just hit the subscribe button. It's really support the channel, and yeah, hopefully see you in the next one.